Hello everyone, I am Bhakti Pandey, working as an assistant professor at IIMT group of colleges. My today's topic for presentation is colloidal dispersion. So in this, we will be discussing about what are colloids, what are colloidal dispersions, types of colloidal dispersions, and the properties of colloids. So we'll be starting with the colloidal dispersion. So then we'll start with the dispersion system first. So what are the dispersion systems? Dispersion systems are one in which we are having two parts. One is dispersed phase and another is dispersion medium. So in the dispersion medium, it is just like the solute and solvent system. Just like a solution, we are having dispersion system. In solution, we are having solvent and solute. Just like that, we are having dispersed phase and dispersion medium. So dispersed phase will be as similar to the solute and dispersion medium will be similar to that of the solvent. So in dispersion system, basically the dispersed phase will be dispersed throughout the dispersion medium. So based on the particles diameter, the dispersion systems were divided into three parts. First is molecular dispersion. In molecular dispersion, the particles size range is less than 1 nanometer. Particles are invisible in microscope, but they pass through the semi-permeable membrane and filter paper. They do not settle down on standing and undergo rapid diffusion. Examples for molecular dispersions are ordinary ions and glucose. So the type of dispersion system is colloidal dispersion. In colloidal dispersion, the size range of the particles are 1 nanometer to 1000 nanometer. Particles not resolved by ordinary microscope can be detected by electron microscope. They do pass through the filter paper but do not pass through the semi-permeable membrane. Particles made to settle down by centrifugation. So these dispersion in this type of dispersion system, the particles do not settle down because of the property of colloids that they colloid with each other. They made collisions with the particles, so they do not settle down easily. They basically show the Brownian motion. That's why they do not settle down easily. So we made to settle the particles via centrifugation. Their diffusion will be slow. An example of such type of dispersions are colloidal silver salts, natural and synthetic polymers. Then comes the coarse dispersions they are having the molecular size range greater than 1000 nanometer. So these are the particles which can be seen under the ordinary microscope. They do not pass through filter paper or semi-permeable membrane. Particles may settle down under the influence of gravity. They do settle down under the influence of gravity and they do not diffuse. The examples of such type of coarse dispersion is emulsions and suspension. So next comes the size and shapes of the colloids. So we are well aware about the colloidal system. Colloidal system, or basically colloids, are the tiny particles that are having the particle size range in between 1 nanometer to 1000 nanometer. So we'll be discussing about the shape and size of colloids. Basically, the particles lying in colloidal size have a large surface area when compared with the surface area of an equal volume of large particles. What is specific surface? The surface area per unit weight or volume of material. Importance of large specific surface area will result in the various properties. For example, platinum is effective as a catalyst only when found in the colloidal form due to the large area which helps in absorbing the reactant on its surface. Other example is the color of colloidal dispersion is related to the size of the particle. For example, red gold solution take blue colors when the particle increase in size. So shape of colloidal particles in dispersion system is very important. So when more the extended size of the particle, more extended the particle, greater its specific surface and greater attractive forces between the particle of dispersed phase and dispersion medium. Basically, flow, sedimentation, osmotic pressure of colloidal system affect the shape of colloidal particles. Particle shape may also influence the pharmacological activity of the colloids. So, here are some shapes of colloids. We can see some of are spherical and globular shape, some are short rods, obsolete ellipsoids and flakes, long rods and threads, loosely coiled threads and branch threads. Here are the images. So now comes the types of colloids. Basically, based on the interaction between the dispersed phase and dispersion medium, these are divided into three types. So first is lyophilic colloids, other one is lyophobic, and last is association colloid or associated colloid. So we'll be discussing first lyophilic colloid. So what are lyophilic colloids? As name suggested, that they are solvent loving. As they are lyophilic, then they are solvent loving, or we can say solvent attracting. Systems containing colloidal particles that interact to an appreciable extent with the dispersion medium are referred to as lyophilic colloids or solvent loving colloids. Owing to their affinity for the dispersion medium, such materials form a colloidal dispersions or SOL. This is primarily due to the presence of solvent sheet around the particles. This makes the dispersion thermodynamically stable. So basically, the colloidal dispersions are having the lyophilic colloidal dispersions are having solvent sheet around them, which makes them more stable, more thermodynamically stable, which lyophobic colloids do not have. So thus the lyophilic colloidal salts are usually obtained by simply dissolving the material in the solvent being used. For example, the dissolution of acacia or gelatin in water or celluloid in amyl acetate generally leads to the formation of the various properties of this class of colloids are due to the attraction between the dispersed phase and dispersion medium when leads to solvation. What is solvation? Solvation is the attachment of solvent molecules to the molecules of dispersed phase, or we can say molecules of colloids or particles or the solute particles. In case of hydrophilic colloids, in which water is the dispersion medium, then this system will be called as hydration. Most of the lyophilic colloids are organic molecules, for example, gelatin, acacia, insulin, albumin, rubber, and polystyrene. Of these, the first four produce lyophilic colloids in aqueous medium, that are hydrophilic salts. Rubber and polystyrene form lyophilic colloids in non-aqueous organic solvents. These materials accordingly are referred to as lyophilic colloids. These examples illustrate the important points that the term lyophilic has meaning only when applied to the material dispersed in the specific dispersion medium. Then comes the lyophobic colloids. The second class of the colloids is composed of material that have very little or very less attraction between the dispersed phase and dispersion medium. These are lyophobic, which are solvent hating. So are predictably their properties are different from those of the lyophilic colloids. This is primarily because of the absence of the solvent sheet around the particles. This makes dispersion system thermodynamically unstable. Lyophobic colloids are generally composed of inorganic particles dispersed in water. Example of such materials are gold, silver, sulfur, arsenious sulfide, and silver iodide. These are stable because of the presence of charge on the particle. Basically, the stability of the lyophilic colloid is due to the presence of the charged particles, because they are having very less or very low surface, low, we can say, size. We can say they are having very small surface area, or they are having very small size. So because of the small size, they are having charge on its surface. So water is used as a medium, the system termed as hydrophobic dispersion. When water we will use in this type of dispersion system, then dispersion system will be known as hydrophobic dispersion. Then come the association colloid, or we can say associated colloid. Missile and the missile concentration, critical micellar concentration is applied in this colloidal, this type of colloidal dispersion. Association, or we can say these are basically amplifiers. Amplifiers generally introduced when we use surfactant term. So in surfactant term, we are already aware about the lyophilic, or we can say hydrophilic head and lyophobic tone. Hydrophilic head and lyophobic tail. So certain molecules or ion termed as amphiphile or surface active agents are characterized by having two distinct regions of opposing solution affinities within the single molecule or within the same ion. So when present in a liquid medium at low concentration, the amphiphile exists separately and of such a size that will fall under the category of subcolloids. Then, as we increase the concentration, aggregation occurs, a narrow concentration range over a narrow concentration of range, and these aggregate may contain the 50 monomers together. When 50 monomers aggregate together, they form missile. So, because the diameter of each missile is an order of 50 angstrom, that will lie under the category of colloidal dispersion or colloids. So the concentration of monomer at which missile formation starts or missile begins to start, it is termed as critical micellar concentration or critical missile concentration. The number of monomers that aggregates to form a missile is known as the aggregation number of the missile. The phenomena of missile formation can be explained as follows. So basically, below the CMC, the concentration of amphiphile going adsorbing in the air-water interface. So as increases the total concentration, amplifiers will rise. And eventually a point reach at which both the interface and the bulk phase become saturated with monomer. This is the CMC. Any further amphiphile added in excess to this concentration aggregates to form a missile in the bulk phase. So in water, the hydrocarbon chain phase inverts into the missile, forming hydrocarbon core and surrounded by the polar portion of amphiphile associated with the water molecules. In non-polar liquid, the polar head facing the inward and the hydrocarbon chain associated with the non-polar liquid. So at concentration close to CMC, missiles will be spherical shape, and at higher concentration they will be laminar missile. So here are some examples of amphiphiles. They are of anionic type, cationic type, non-ionic type, and ampholytic type. So these are the examples. Then comes the properties of colloids. So there are various properties of colloids, and they are having optical properties, kinetic properties, as well as electrical properties. So in optical properties, we have other sub properties, which are the Tyndall effect, electron microscopy, light scattering and turbidity. And in kinetic properties, we are having Brownian motion, diffusion, osmotic pressure, sedimentation, viscosity. And in electrical properties, we are having electrophoresis, electroosmosis, sedimentation, sedimentation potential, streaming potential, electrical double layer, and Donan membrane effect. So first of all, we'll be starting with the optical property. So very important and very classic property of the colloid is a Tyndall effect. What is a Tyndall effect? When a strong beam of light is passed through the colloidal solve, a visible cone resulting from the scattering of the light by colloidal particles is formed. So this is Faraday-Tyndall effect. Basically, when we pass beam of light through the colloidal dispersion, the particles absorb, particles will scatter the light and illuminate them. So the scattered beam form a cone of light known as Tyndall cone. The Tyndall effect is not shown by true solution. Only colloidal solution will form a Tyndall cone. No true solution, no other homogeneous solution will form any Tyndall cone. So the ultra microscope developed by Sigmoidi allows one to examine the light point responsible for the Tyndall cone. An intense light beam is passed through a sol against dark background at right angle to the plane of observation, and although the particles cannot be seen directly, the bright spot corresponding to the particles can be counted. So this is the Tyndall effect. Now we will discuss about one or two kinetic property of colloid. So first kinetic property of colloid is Brownian motion, and this is the very important kinetic property of any colloidal particle. So what is Brownian motion? Who have given this phenomena and how? So Robert Brown was a scientist, was a botanist who had discovered this phenomena in 1827 in pollen grains. When he suspended some pollen grain in water, he observed that they do not remain in rest, but they are continuously moving randomly in all the directions. So later on, he observed that the colloidal particles are moving at random zigzag motion. So this type of zigzag motion is basically known as the Brownian movement or Brownian motion. Brownian motion describes the random movement of colloidal particles. The continuous zigzag movement of colloidal particles in the dispersion medium in colloidal solution is called Brownian movement. The erratic motion which may be observed when particles as large as about 5 micrometer was explained as a resulting from the bombardment of particles by molecules of the dispersion medium. So the other kinetic property of colloids is diffusion. So basically we all know what is diffusion. Diffusion is a mass transfer process. Particles move through the higher concentration region, from the higher concentration region to the lower concentration region until equilibrium achieved both the sides. So diffusion is a direct result of Brownian movement here. According to Fick's law, the amount that is denoted as dq of substance diffusing in time dt across a plane of area S is directly proportional to the change of concentration dc with a distance traveled dx, which is written by Fick's law. So Fick's law indicate that dq equals to minus ds dc upon dx dt. So here d is the diffusion coefficient and the amount of material diffusing per unit time across the unit area. So when dc upon dc called, the concentration gradient is unity. Now comes the electrical properties of colloids. So in electrical property, we are having electrophoresis. So what is electrophoresis? It is the movement of charged particles under the influence of electric field. So due to the presence of a particular type of electrical charge, the colloidal particles present in the colloidal dispersion move towards the particular electrode under the influence of an electric field. The direction of movement of colloidal particles is decided by the nature of charge present on them. If they were having positive charge, they will move towards the negative side of the electrode, and if they are having negative charge, they will move towards the positive end of the electrode. So this phenomena is called as electrophoresis. Now electroosmosis. So this is electrophoresis. Then what is electroosmosis? Electroosmosis is just like electrophoresis, but in electrophoresis, the movement of charged particles are there, and in electroosmosis, there is a movement of dispersion medium under the influence of electric field. So these are the properties of colloids we are discussed. Thank you so much. Thank you for giving some time for the presentation. Thank you so much, everyone.